Hey everybody, let's continue our discussion about torque. So let's say you have some object that's rotating and it has some angular acceleration, rotating about this point right here. And let's say there are a bunch of point masses everywhere. And let's just add them all up. So I'll just pick one of them. I'll call this mass M, and then we'll just sum. So let's sum the torque for all of these discrete masses. So like M1 over here, M2 over here, M3 over here. So I'll just draw pictures for one of them. So what is torque? It would be R cross F. Right, so R cross F for every single one of these masses, if we have n of them. Okay, and then we can decompose F into perpendicular and parallel, parallel, perpendicular, and then, if you do distributive property, R cross the parallel component would be 0, because, right, the cross product of parallel vectors is 0, right? So this would be 0. So all you're left with is R cross F perpendicular, which, let's just say, the magnitude. Okay, so this is a vector, right? So if we're just concerned about the magnitude, I'll just write it like this, without the vector, right? Just the magnitude. Then it's just RI F times F perpendicular, like that, right? The parallel component doesn't do anything. Okay, force is mass times acceleration, but only the perpendicular component. So only the perpendicular component would be tangent to the path, right? So if we're rotating about some point like this, here's R, here's, let's say, F, but we decompose it into, let's say, perpendicular, parallel. I'll just draw it like this, right? And then the acceleration. So this is the acceleration perpendicular to R. This is the acceleration parallel to R. This component of the acceleration is centripetal. That's not contributing any torque. Only this one, which is tangent to the path, right? It's tangential to the path. And then if you look back a little bit, remember the relationship between linear things and rotational things? If you have some arc length S, how does it relate to the angle? Like this. If you take a time derivative, the velocity is proportional to the angular velocity. The tangential component of acceleration is proportional to the angular acceleration. So this part right here is this, relates here. Right, so some torque is R, the acceleration, R alpha, right here. The tangential component of acceleration turned into R alpha. So really what we have is R squared alpha. Okay, but imagine you have, we had this discussion before, like a merry-go-round, and then two people lying down on the merry-go-round, let's say. And then it rotates 90 degrees, like this. So who goes farther? This person goes farther, or a longer arc length than this person. So in the same amount of time, this person is going faster, and then that same change in speed, this person is accelerating more. But for rotation, they both rotated the same amount, 90 degrees, pi over 2. So in the same amount of time, they have the same angular velocity and the same angular acceleration, as long as they don't move around. So this is valid for an object that doesn't change its shape, that doesn't deform. So for an object that doesn't deform, called a rigid body, the angular acceleration is the same. Like every molecule in this disk is rotating with the exact same angular acceleration, which means over here, I can pull that out of the sum. So I can take this out of the sum. Here, it's the same for everybody. So you see this right here? That is the very definition of moment of inertia. Right here. It looks familiar. That's moment of inertia. So this is a brand new law. This is Newton's second law for rotation. Let me write above it what we had before Newton's second law. Some forces equals mass times acceleration. See how it looks analogous for rotation? Some torque equals moment of inertia times angular acceleration. So let's say we have like an Atwood's machine system. So there's a pulley, let's see, connected to a block over here. I'll call it M of mass M1. Let's say this is smooth. And then on this side, there's another block hanging. And say the pulley, let's model as a disk. So it's a disk of mass M, D for disk, and radius R. And then we look in the table of moments of inertia, and we find that for a disk, the moment of inertia about its own center of mass is 1/2 mr squared. Okay, so let's say this block slides to the left, this block slides down, and then the disk rotates counterclockwise. Let's solve for the angular acceleration of the pulley. Okay, so what do? We draw the free body diagrams. So for this block over here, there's tension in the string and there's weight. For this block over here, I'll draw it and over here. There's tension in the string, normal force, weight. There's no friction because it's smooth. And then for the pulley, now the pulley has mass, so it needs its own free body diagram. So here's the pulley. Draw all the forces acting on the pulley. So there's the string here, which is the same one here. There's the string here, which is this one here. And then see this bearing that the pulley is rotating on? There's some normal force. I'm not sure what direction it is. Some direction. I don't know what angle. So this is some unknown angle, some normal force for the pulley. And the pulley has weight. Okay, so mass of the pulley. Okay. And before, when we had an Atwood's machine system like this, we're assuming the tension was the same everywhere. So the tension here was the same as the tension here. We can no longer make that assumption because now the pulley has mass, has a moment of inertia. So the tension here for block 2, the tension here for block 1 are no longer equal. We can no longer make the assumption that they're the same. Okay, so that's T1 over here, T2 over here. Okay, so now we have our 3 free body diagrams. So block 1 is going to go this way, and block 2 is going to go this way. So I'll pick a coordinate like that. And then the pulley is going to rotate this way. So I'm going to pick a coordinate system. Let's say you can choose the origin wherever you want. I'm going to pick it at the center of mass. And let's say if I want Z this way, then I could pick, for example, X here, Y here, and then in which case Z would be counterclockwise. So Z would be this way, out of the page towards you. Okay, so you know how to do these, right? Some forces X. Over here, some forces, right? You've done this before, so. And then Y direction. Okay, so this block is only going in the X direction. AY is 0. All right. Here, the new thing, some torque, because let's practice using this brand new, right? This is Newton's second law for rotation here. So sum torque about wherever you want. So you can sum torque about here, or here, or here would be good choices. Because if you sum torque about here, this tension doesn't produce any torque. If you sum torque about here, this tension doesn't produce any torque. But if we sum torques about here, the normal force doesn't provide torque, and the weight doesn't provide torque. So I think that's a clever choice if we sum torque about the center of mass. Okay, so this doesn't produce any torque. This doesn't produce any torque. This one does. And so what is the torque by tension T2 is this lever arm times this force. Right, so this lever arm is radius R times this force. And it's like this because they're perpendicular. And then that would create torque which way? About this point, this force creates torque counterclockwise, which is in the positive Z direction. So this is positive. Okay, now the torque by this, the lever arm is here, and these are perpendicular. So R times T1, and that will cause a torque this way, which is in the negative Z direction. So I'm going to put a minus sign here. And that's it. Sum of torque, it's only the two of them. And then equals I alpha. Which I? Because I sum torque about the center of mass, I need the moment of inertia about the center of mass. If I sum the torque about somewhere else, like over here, then this would have to be the moment of inertia about over here. Okay, so let's take a look at what we know and what we don't know. Okay, so we don't know, let's say we're given all the masses, and then the radius of the pulley, right, then these are unknowns. And one more thing, how does this acceleration relate to this angular acceleration? If you go back, remember how linear things relate to rotational things? Like if there's some arc length S, how does that relate to angle theta? If this is some radius R, S equals R theta. Right? And then take a time derivative for constant radius. This becomes V. This becomes omega. Take one more derivative. Because this is tangent to the path, it's the tangential component of acceleration. Then it's time derivative of angular velocity, angular acceleration. Okay, so this is true for the acceleration tangent to the path. So now, if you take a look at this block, it's accelerating this way, right? And now look at the pulley. That is tangent to the path. Look at this block. It's accelerating this way. And look, that is also tangent to the path. So this acceleration is tangent to the path. This one is also tangent to the path. And so how does it relate to the angular acceleration? Like this. Just like this. Okay, so then we have this 2, 3, 4, 5 equations. And if we want to solve for the angular acceleration, we'll then finish underlining the unknowns. So this, okay. I definitely need equation, here. I need equation 1, 2, 3, and 4. Okay, so which has the most unknowns? This one. So because this equation 2 has the most unknowns, I want to substitute things into it since it has the most. Okay, so let's solve this for t2. So from equation 1, t2 equals m2g minus m2ax. And look right here, ax equals r alpha. So I'm just going to write r alpha. Okay, and then look over here from equation 4. T1 equals m1 ax, and ax over here is r alpha. Now I can take these and substitute them here and here. Okay, so let me do that. I could probably clean this up a little bit, right? R times T2 minus T1. And then what's the moment of inertia of the pulley? Right here. Right here. 1/2 mr squared. So I'm just going to write that over there. 1/2 mr squared alpha. And why don't I just move this r over here? Okay, there we go. So clean that up a little bit. Now I can put this here and put this here. So let me do that. m2g minus m2r alpha minus t1 m1r alpha equals half. Oh, this is for the pulley. R alpha. And what is the unknown? Right here. Right, so then you just take these two, move it on that side, solve for alpha. So I'll just finish that up. So take these two, move it on the other side. So let's see, we have some common factors, r alpha. Okay, and then I'll move these back in the denominator. So alpha equals r. Okay, so there is the angular acceleration of the pulley. Okay, so let's do some more examples in other videos. I'll see you on those.